In this video, we're talking about inverse functions. Specifically, we'll be talking about how to identify whether two functions are inverses of each other. We'll talk about finding inverse function values on tables and graphs, and we'll talk about how to actually find inverse functions, or really inverse relations, whenever you're given a function. Because not all inverses of functions will be functions themselves. So here's the main definition to know. F of x and g of x are inverses if f of g of x is equal to x, and if the opposite is true, g of f of x is also equal to x. What this means is g of x would equal f inverse of x. So when you see this f to the -1 power, just know that's notation for the inverse function of f. Let's talk about why this works out real quick. If g is just f inverse, then if we replace the g's with f inverse, the idea behind f and its inverse is that they basically oppose each other. Like, they have the opposite effect on whatever the input is. So if you input x and then f inverse acts on it, but then f acts on that, then these essentially cancel each other out and you're left with x. That's why we're left with x. And same thing the opposite direction. If you plug x into the function f, but then you plug that into f inverse, then again, f inverse will kind of reverse the effect that f had on x, leaving us with just x. Now let's demonstrate identifying whether these functions are inverses of each other or not. Again, what we want to show is that f of g of x is equal to x and g of f of x is equal to x. So to find f of g of x, we're going to start with our function f, we're going to leave a space for x, and then we'll plug in g. So does this equal x? Well, if we drop the parentheses and then do -4 plus 4, we are just left with x. Let's do the opposite, g of f of x. G of x is x minus 4, and in place of that x, we are plugging in f, which is x plus 4. Same idea, drop the parentheses, 4 minus 4 is 0, so then we're just left with x. So because this was equal to x and this was equal to x, f and g are inverses of each other. Let's try another example here with two new functions. Are f of x and g of x inverses of each other or not? We'll find f of g of x first. So we start with f, plug in g, and this is pretty much it. We can't really simplify this much because we'd have to expand this out by squaring it and then adding 6. I don't know, it doesn't look like it's going to lead to just x. So now let's just confirm this by finding g of f of x. G looks like this. We plug in f in place of x. We can't really simplify what's going on here. In other words, this is not going to equal x by any means. So in this case, we say no, these are not inverses of each other because f of g of x does not equal x, nor does g of f of x. Any idea what small change we could make to g of x so that f of x and g of x would be inverses of each other? Take a moment to think about it, and then I'll give the answer away. So the small change we could make is just to extend this square root over the -6. And so instead of just having x under the square root, we now have x minus 6 under the square root. Let's talk about how that's going to change things. Right here where we plugged in g of x, we would now have square root of x minus 6, the whole thing squared. So if we started to simplify this, this square with the square root would cancel each other out. We would just be left with the x minus 6 that's on the inside. We would add that other 6 back. We'd cancel the 6's and just be left with x. Now down here, if we started with just g would now look like this. And then we would plug in f wherever we saw x in the function g. So we'd have square root of x squared plus 6 minus 6. The plus 6 and the minus 6 cancel. And then you have the square root of x squared, which also equals x. And so that's the small change we could make to g of x to make it so that these functions are inverses of each other. And we'll do just one more here. This one is totally for you to try. Take a moment to confirm whether these functions are inverses of each other or not. I'll go ahead and work it out. F of g of x, we start with f of x, plug in g, go ahead and distribute the 2. We get 1x plus 1 minus that 2. 1 minus 2 is -1. So right away, we get x minus 1, which is not equal to x. So really at this point, if you got that f of g of x was not equal to x, there's no need to check g of f of x to confirm, because if one of them is not equal to x, then that is enough to say that these two functions are not inverses. But just to demonstrate, I'll go ahead and find g of f of x. We start with g, we plug in f, we distribute, we get 1x minus 1 plus 1/2, which then equals x minus 1/2, which again is very close, but it is not equal to x. So again, no, these are not inverses of one another. But once again, follow-up question for you. What small change could we make to g of x to ensure that f of x and g of x would be inverse functions of one another? All we have to do is change that 1/2 to a 1. And let's demonstrate what happens. This 1/2 turns into a 1. We distribute the 2. We get x plus 2, and then we subtract 2. 2 minus 2 leaves us with x. And over here, this 1/2 would have gotten changed to a 1. So once again, we distribute. We get x minus 1 plus that new 1. Negative 1 plus 1 cancel and leave us with just x. Let's talk about finding inverse function values from a table. Let's say you have this table of x and f values. Keep in mind f of x is pretty much just your y values. When going from a function to its inverse, the main idea is that you are swapping the x and y values. When you swap your x and y values, your y values become your x values and your x values become your y values. And these new y values are your inverse function values. So let me put it this way. If from this table we know that when x is 2, f is 5, that means we also know that when x is 5, f inverse is 2. Notice this ordered pair just gets swapped around if you want to know the ordered pair that's on the inverse function. Once again, if 4, 9 is a point on the original function's graph, then 9, 4 will be a point on the inverse function's graph. So now let's find some values. What is f of 3? Well, from this table, when x is equal to 3, f is equal to 7. So f of 3 is 7. So in that case, what is f inverse of 7? Well, that would be 3. So the idea is the inputs of your inverse function, like this 7, come from your f of x values. And so we see the 7 here, and we know it corresponds to an x value of 3, so 3 is the value of f inverse. So to find an original f value, we know to plug in 3, which means we look at the x value of 3, and it corresponds to an f value of 7. For f inverse, we just do the opposite. If the input is 7, we look at the f values, find the 7, and see that it corresponds to 3. So it's just doing the opposite. Let's try another one. What's f of 5? Well, f of 5 is 11. When x equals 5, f equals 11. How about this? What's f inverse of 11? Well, that's going to be 5. Another way to think about this is instead of f inverse of 11, we know that 11 was equal to f of 5. So check out this thing that's kind of cool. If instead of writing f inverse of 11, we write f inverse of f of 5, think about the effect that f inverse has on f. F inverse and f just cancel each other out, and it just leaves you with 5. And so that's kind of why f inverse of 11 equals 5, because f inverse of f of 5 would allow those to cancel and just leave you with 5. All right, let's try one more. This time we're not finding any f values. Let's start by just finding f inverse of 5. If you said 11, I'm afraid that's incorrect. Keep in mind, we're finding f inverse, not just the f value of 5. So f inverse of 5, we would look here and identify its corresponding x value of 2. Keep in mind, once we swapped x and y, this became y, this became x, and the y that this became was f inverse. So that's why when you're plugging in something like 5 to f inverse, you get the f inverse value from this top row. Alrighty, how about f inverse of 13? Hopefully it's obvious. That one has to be 6. This is the only place 13 is on the table, and that corresponds to 6. Alrighty, new chart here. Real quick, can you tell me what f of negative 2 is and what f inverse of negative 2 is? Well, when x equals negative 2, f is equal to 10. To find f inverse of negative 2, we look down here. We see when f is equal to negative 2, it corresponds to an x value or f inverse value of 0. Let's try 2 more. What is f inverse of 1 and what is f of 1? Well, looking down here, f inverse of 1 is 1. And looking up here, f of 1 is 1. Not too hard, right? All right, last one. What's f of 2 and what is f inverse of 10? Well, when x is equal to 2, f is equal to 10. Easy peasy. So you might right away say, well, then f inverse of 10 has just got to be 2. Because when f is 10, x is 2. But wait a minute. When f is 10, x is also negative 2. So which answer is correct? Well, actually, they're both correct. And the reason is f inverse must not be a function. Why is it not a function? Well, it goes against the definition of a function. The definition of a function says that one input creates one and only one output. But in this case, this one input of 10 is creating more than one output. So this brings up an interesting idea where if you have a function f of x, its inverse might not always be a function itself. So the function that these table values come from is 3x squared minus 2. Let's check out a graph of this. Let's start by graphing some points on the original function, -2, 10, -1, 1, 0, -2, 1, 1, and 2, 10. So we have our parabola. It's a little wonky, but it looks fine. Now let's graph the inverse. Now how do we graph an inverse? Well, if we know the ordered pairs on the original function, what do? We just swap the x and y values. So all these f values that were down here become the x values for the inverse, and all these x values of the original become the f inverse values for the inverse. So now let's plot some of these. We have 10, -2, 1, -1, -2, 0, 1, 1, and then 10, 2. So now when we connect these points, it looks something like this. Once you visualize what this inverse looks like, you can really say this is not a function because it fails any vertical line test you do. It is infinitely failing any vertical line test you do. So you might notice some symmetry between these two graphs. From the original to the inverse, it looks like the same function just turned on its side. And so a quick way to tell if an original function will have an inverse that is also a function is to do what we'll call the horizontal line test to the original function. Keep in mind, the original function is a function because it passes the vertical line test. But what happens when you try the horizontal line test on the original function? A horizontal line will pass through more than one point. So we would say it fails the horizontal line test. And because it fails the horizontal line test, that's why the inverse relationship is not a function. So basically, if you were given the original function and they asked, does this have an inverse that is also a function? You would say, no, it fails the horizontal line test. So in addition to plotting points from 2, 10 to 10, 2, and from -1, 1 to 1, -1, and in addition to the horizontal line test indicating whether an inverse is a function or not, the last important thing to point out about graphs of inverse functions is that the graph of an original function and its inverse will be symmetric about the line y equals x. So for example, if you were to mirror this point over this line, it would end up right here at 10, 2. If you were to mirror this point, -1, 1, over this line, it would end up at 1, -1. If you were to mirror this point that's right here over this line, it's going to end up right here. So that's sort of the idea. So basically any point that's on this side gets reflected over and ends up over here. Any point that's on this side would get flipped up over that line and end up over there. So that's pretty much everything with the graphs. Now let's talk about how to find the inverse function when given another function. If you were given the function f of x equals x plus 4, here are the steps. Rewrite f of x as y and then swap x and y, just like you would swap x and y with ordered pairs. Once you have this new y is f inverse. And so you want to solve for f inverse by getting f inverse by itself. In other words, you want to get y by itself. So the only step we need to take to get y by itself is to subtract 4. So we get y equals x minus 4, which means f inverse of x is x minus 4. Let's try another one. F of x equals 2x plus 2. Let's find the inverse function. Rewrite f of x as y, swap x and y, and then solve for y, because that y is f inverse. We subtract 2, and then we divide by 2. We could call it x minus 2 over 2, or we could call it 1/2 x minus 1. Once again, this is y, and that y is equal to f inverse of x. Take a moment to find the inverse of this function on your own. Let's talk through the steps. F of x is y, swap x and y, now get y by itself. We eliminate the square root by squaring both sides. So we have x squared equals y minus 7, and then we add 7 to get y by itself. This is f inverse of x. Now what do you know about the graph x squared plus 7? Maybe you know that x squared is a parabola and the plus 7 means it'll have a y-intercept of 7. So when you see this function, this inverse function, the beautiful thing is this inverse function is in fact a function. But what about its inverse? What about the original function f of x? Is that going to be a function? Well, think about this. F inverse passes the vertical line test no matter what. So f inverse is a function, but because it fails the horizontal line test, that means the inverse of this function is not a function. But the inverse of f inverse is supposed to be just f of x. So like we saw earlier, if we were to graph the reflection of this image over the line y equals x, we would get something along these lines, a parabola opening to the right with an x-intercept of 7 instead of a y-intercept of 7. So now I'm confused. Wasn't f of x just the square root of x minus 7? I thought this is a function. Is this the graph of square root of x minus 7? No, it's not. Square root of x minus 7 is actually just this portion. And the portion below the x-axis is actually the negative square root of x minus 7. And so what does this mean? How do we ensure that both f and its inverse, or both f inverse and f, its inverse, are functions? There are cases where you might be asked about like domain restrictions of f or its inverse to ensure that both f and its inverse are functions. And so in this case, what we would want to do is restrict f inverse to x values greater than or equal to 0. What this does is have us consider the graph of f inverse, but only from x values 0 to infinity. So what that means is we get rid of this left side of the function. So now look at what happens when we get rid of the left side of the function. Let's ask ourselves again, does this function pass the horizontal line test? Yes, it does, because every horizontal line only intersects the function once. So now when you graph the inverse of this function, you actually only get this orange part here, because when this is reflected over the line y equals x, it becomes this function right here. So now both a function and its inverse are functions. I hope this makes sense. This was just a rough intro to inverses of functions. If you have any questions on anything, please let me know.